Okay. So good afternoon. So, any questions from yesterday's course? From yesterday, the yeah, we finished the all the necessary method or the task for convergence or and divergence. Okay. So, any questions related to yesterday course? I think so far so good. All right. Maybe we start with some review, okay? On this strategy. Okay? We did this yesterday. How to? But let me add more questions. Okay. Let me add more.
Maybe you can show us solutions of those examples.
I think solutions should be easy, right?
It should be easy, but
Let me add more. Okay, let me add more.
it's easy for you.
Okay, let me just add more, and then you see if you still have time. We'll try to answer all. Okay, so questions is a typical determine the series converge or diverge. So first one is wait, one more. Okay, let me give you 5 minutes to try. 5 to 6 minutes to try. Any idea for the first one?
Interested?
Maybe one day. So this one is also. One over n.
Okay, so if we look back on the strategy, the first thing we can scan to find which method is divergence test, right? We could take divergence test. Let me write here, okay? So you need to remember. So if the test is considered as if the series converge, then its limit is equal to 0. But it's not work reversibly. So if the limit is 0, the series is not necessarily converged. But if limit is not 0 or it's not exists, then the series diverge. Okay. So when you find out that the limit is 0, it doesn't mean it's converged. So we need to try another method. Okay. So remember that. It's different from the sequence. In sequence, if your limit 0, that means it's converged. Okay. But the series is the summation of the sequence, right? So it's a little bit different. So the first 3 questions is actually going to be using comparison method, the best way, I think. Okay. If you can think another way, maybe that works. But I think it works well for the first, second, and the third question. It works well with the comparison method. Okay. So the first one, notice that it starts with n equal 2, because when it starts with n equal 1, it is 1 over 0, right? But if we start with n equal 2, we have 1 over ln 2 plus 1 over ln 3 and so on and so forth, okay? Now, we can take this, take another series. For example, that we know, let's say the same constructions like this, okay? Let's say that series, a harmonic series, okay? Which this is conclude to be diverged, right? By the P series, you can see from the P series, it's just a power of 1. And then we can conclude that this is greater than 1 over n, right? Because ln n, if you start from 2, we have a decimals here, of course it will be greater because it's reciprocal. So it will be true, right? So because of this, then as a conclusion that this series diverge as well. So also diverge. Okay. Now the second questions, it has actually it has 2 components. We can relate the series with 2 series. Fine. So we can relate to this e power of n, okay, and we can plus Okay. And for the first one, if we break down this series, let's say take a few terms, 1 over e plus 1 over e squared, right? Plus 1 over e cubed plus dot dot dot. And we know that this will be geometric, right? Geometric series. So R is 1 over e, okay? And we know that this is less than 1, right? Converge. This one is converge, this one is converge. This one converge, convergent, because R is less than 1, okay, for the geometric series. But then we need to look on the whole thing, the whole series. The whole series has a cosine. This part, the second part here.
We can just compare it with.
Yeah, we can compare. We can compare. Yeah, we can compare. So we can compare. So compare that the cosine n over e is less than or less equal with the 1 over. Or we can directly, right? We can directly, or we can input all together 1 plus cosine n, okay? And then let's say we are comparing this to 2, okay, to make sure that 1 plus something is approaching 2. Okay? We can also do this directly, okay? So, and we can say that this will be converges by direct comparison test.
What is 2 over e over n?
This is just my approach for this plus cosine.
Yeah, why is it convergent? That's right part. Yeah.
This one is
Yeah.
the same geometric series.
The same one.
The same one, right? The same one. It just has a constant too.
L.
Yeah.
Sorry.
Yeah. Okay. Let me write here. This is also convergent geo series with R is less than 1. Now the interesting one is the third question. It's sine with the 1 over n. As I mentioned before, this could be solved by the comparison, but not direct comparison. So if we look at this sine, and if you remember the limit comparison test, it has limit, it has sine, and it's 1 over n. If we divide with 1 over n. So let's imagine that there are some other series that we call 1 over n, which is diverge, right? Which is diverge. Diverge harmonic series, right? So we try to break down the series with the limit comparison test. So we take the limit n approaching infinity of, let me write an over bn. Okay, an being the sine, or maybe just sine. Okay. So take the limit, and here we have sine 1 over n over 1 over n. And it's equal to 1, right? Okay. This is from the limit identity for sine x over x. Okay. And don't forget, okay, in limit comparison test, perhaps you maybe mix up with the ratio test. In ratio test, if you get equal 1, it's not conclusive. But this is limit comparison test, which we are going to look on the positive value here. And this is sufficient. Right? This is fit with the test. And because it's fit, then as a conclusion, the series also diverge due to limit comparison test. Okay. What's that? Oh.
Sorry.
It's okay. I thought someone was screaming. Let me make this smaller. Let me write in the right side. Okay. Maybe if you forget the limit, this is the identity for the sine. Okay, how about the last one? Again, if you see, if the series can be separated, maybe try to look one by one. Okay, so if we take this into separations, so this is the first one, and this is the second one. And both series, if you see, this is from the P series. Okay. We know this is, the P is greater than 1, right? And we can conclude that this will be converged. While the other one, if we see, this is 1 over 3 plus 1 over 3 squared plus 1 over 3 cubed plus . And this is a geometric, again, this is geometric series with R equal 1 over 3, which is less than 1. And we know that this is geometric and convergent. So the sum of both are converged. So the series is convergent. Okay, now for the next section, we're going to study the what we call the power series. Okay, the power series. Okay, now let's move to the next page. Maybe wait for a couple minutes if you want to write. Okay, now let's start with the title is Power Series. Okay, let me start with if we take a series, let's say from n equals 0 of x with power of n. This is just a normal geometric series, right? This is 1 plus x squared plus until the x with power of n, right? And of course, from the geometric series, we know that this will be converged when it is going to be in between this, or x is generally an absolute value in between these numbers, and diverge if the x is greater or equal 1. Okay. And this will be true, and if we take x equal half or equal any constant, we will get the convergent series. We will get the convergent series, okay, through the again the geometric series, right? So in power series, actually, what we are going to deal with is the term will have sum of a constant n and xn. This is what we call the power series in general. So let's say it starts from 0 to infinity, and this will be from c0 plus c1 x1 like that, plus c2 x2 plus c3 x3 plus that. And again, we have now c x as a variable, and cn is constant. We call this coefficient of the series. So the idea behind this power series is we are going to evaluate some series that has x and n. So we are going to test what kind of x that makes the series converge or diverge. Before, what we test is directly a constant and n, right? Directly the n. But now we add more variables, which is x. Okay. That means n still act as like usual in the series. We can test n from equal some numbers up to infinity. We can test a few terms with n. But now, what we are going to observe is x. Okay? What kind of x do we want to make the series converge or diverge? Okay. And you can check when we take the x, for example, if x is greater than 1 for the series here, then it will be, let's say, 2 with power of n. Okay? And you will see that this is going to be increasing large and large, right? So 1 plus 2 plus 4 plus 8 plus dot dot dot, right? It's going to be increasing and increasing. If x is less than 1, say half, then we are going to see that this is going to be converge. It's like the Zeno, the paradox that we saw at the beginning of our chapter 11, right? So now let's imagine this x, okay, is written within x minus a. Okay. So let me write here x and cn and x minus a with power of n. This is more general form for the series. So this is c0 plus c1 x minus a plus c2 x minus a squared plus dot, 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 dot. This is what we call the power series in x minus a, or power series centered at a, or power series about a. Let's say this is going to be the next part. Now, because we write the terms x in terms x minus a, because we write like this, it gives you some sort of understanding that the convergence is like having some sort of range, some sort of because the convergence, like previously, we decide something is converge or diverge directly, right? From the test, you can take the divergence test, the p-series, and all over the test. And in here, what's happened is, when the series is converged, we want to know how the convergence is, how the radius of the convergence will be, because the convergence is not always going into one point, but maybe it has some range, and now we want to look and observe those range. Okay, now let me give you some idea, okay, before giving you the conclusions. So let's say we are going to see the series Okay. Maybe the question is what values of x does the series converges? So let me take this line here. Okay. So it's asking what kind of x do we want to make the series here converge? Of course, you can try some x's, but we can sort of try to test the series itself with one method that we studied before, which is the ratio test. That's the best way to test all the power series is going to be the ratio test. So we are going to take the ratio test and take on the series. Okay. So test with ratio test. So let's say an is the x minus 3 over n, right? And ratio test is start with an plus 1. You may write limit directly if you want. Limit n going to be infinity. Okay, x minus 3, n plus 1, n plus 1, and then here is n. Okay. I think we can cancel out this part, right? And this will be x minus 3 going there. You can see that we have now the x minus 3 x minus 3 and then we have n over n plus 1, right? We can focus the limit on n, right? So x minus 3, and this limit is going to be written as limit and we can write this is maybe I'll remove the absolute value for n, so we can write divide by n, it's 1 plus 1 over n, so the limit is equal to 1. Okay, so as n, so we can make conclusion as n getting larger, it's getting to, the series is getting to x minus 3. Okay. So we know that from this ratio test. Okay, let me write so based on ratio test, so based on so let me write here, this is x minus 3. So based on ratio test, when x minus 3 less than 1, this is going to be convergent or absolutely convergent, if you remember, absolutely convergent. When x greater than 1, this is going to be divergent. And we take this into our considerations. So when x minus 3 in absolute value less than 1, which means this is going to be negative 1. So this is going to be 2x 4. So converge from this range, okay? Range of values. So converge. And diverge for when the absolute value is greater than 1, which is x is less than 2 or x is greater than 4. So this will be diverge. So if you want to know when the series converge, that is from 2 to 4. But it's not complete yet. It's not complete yet. The ratio test, remember, the ratio test, when it's equal 1, it doesn't give any conclusions. So we need to test separately. We need to test separately. So let me move this. Okay, so test when equal 1. Okay. So we need to consider, okay, so we need to consider x equal 2 and x equal 4. Okay. And we put these 2 and 4, each one to the series. Okay. So when x equal 2, the series become, what is the series? X minus 3. So it will be minus 1. So it becomes this series from n equal 1. Which is, this is the alternate series, which is converged by alternate series, right? And then when x equal 4, this series becomes 4 minus 3 is 1. So 1 over n, just normal harmonic series, which is diverge. So the true conclusions, converge, or maybe the series converge when x is, we are going to include 2, so it's going to have equal now, but exclude 4. Okay, so this is the final answer. Maybe cut this over. Okay, we may have a break. Okay. I feel lazy to write, so let me copy. Okay, now to continue for what we have before, so let's try another series. Okay, and from all these examples, we are going to draw conclusions. Okay. Okay, two series, same questions. What values of x does the series converge? And again, we start by taking the ratio test. Okay? Start by taking the ratio test. And then see where the x values converge. Okay? So in ratio test, if you remember, we may have the ratio that is less than 1, greater than 1, or equal 1, right? Okay, so taking ratio test, let me start with this. Taking ratio test, so take limit. This will be n plus 1 factorial. This is going to be x n plus 1. This is n factorial and x power of n. And remember that when you have n plus 1 factorial, this is equal to n plus 1 multiply n factorial. Okay, so we can remove the factorial and cancel with this one, and we can see that the ones left is n plus 1. The same thing, we can cancel the x with power of n, and the only thing left is x. I'll forget this value. So from this sort of calculation, we see that this is going to be x, and then having a limit as n getting larger for n plus 1, right? Now what conclusion from this part? Okay. So we have an absolute value of x and n plus 1, and this limit is getting larger. So let me rephrase the question. If you see this as a result, what kind of x to make this converge? What numbers? Yeah, 0, right? Okay. So the only way this to be converged, okay? The series, let me write completely, the series diverge if x is not 0. And the only way the series can be converged, so the series converge only when x equals 0. And now the next question. We have this series. Okay. And do the same thing. If you want, you can take the ratio test. But please careful on these 2n factorials. You need to be careful when you exchange n with n plus 1. Okay. I think my suggestion is take the brackets and be careful when you're substituting the n. Okay. So take ratio test. So this will be x n plus 1 over, now you need to be careful here, so this is 2, okay, and then n plus 1 and then factorial. And this is multiply with 2n factorial and x to the power of n. Immediately we can cancel the x with power of n. How about this factorial? Let me rephrase this in more detail. Let me write x in the front. So let me factorize x outside limit. Okay. And we have 2n factorial. And in the denominator, take a look. This will be 2n factorial and then 2n plus 1, 2n plus 2. And canceling this out. We are going to see absolute value of x limit So if you see the last one, no matter what x will be, the limit will always getting 0. So we can say that the series converges for all values of x. So the series converges for all x, for all values of x. You can think that if you maybe a little bit having difficulty with the factorials, we can see the factorials as this 1, so 2n plus 2, 2n plus 1 and 2n factorial. So we give notes. Okay, so we have 3 examples and we have 3 conclusions. Okay, we have 3 conclusions. So those conclusions from these 3 examples we can rewrite in terms of the interval of convergence. Okay, so this interval of convergence, which one is this? Okay. So for a power series, there are 3 possibilities. A series converges only when x equals a, which means this is becoming 0, or the series converges for all x, as we mentioned the last one here, or there will be a positive number such that the series converges when its absolute value of x minus a is less than the ratio, less than some value that we test from the ratio test, and diverge if that is greater than r. So with these 3 possibilities, then you can draw conclusions from a power series. So that is one thing. R, okay, here R refer to not only ratio, but we can call also this is radius of convergence. So the ratio that we went into is actually what we call the radius of convergence. So the interval of convergence, we can have some possibility that is just that, okay? Or this way, or this one. Notice that there will be some slightly change on the brackets. Okay. So as we solve, if you remember the example before in the previous slides, we take the radius of convergence. We find the ratio, right? We find the ratio, and suppose it's less than 1 to make it converge. We get this, right? We get this. But we need to also test when it's equal 1, okay? Because it's not yet completed. So we may have this four possibilities. Okay? If you feel maybe too much terms, let's see if we can draw this in more visuals. Okay. So imagine that A is in the center, that's what we call the power series center at A. Now the radius or the ratio that we found is really radius in terms of this distance. And the convergences is going to be in between this. What we want to know is for sure how is the point at its endpoint. That's why we need to equaling the or we need to pass the ratio when it's equal to 1. Let me write here that this need to be tested more. So this one here, the endpoints need to test. So we can conclude which one that are in the interval. So again, how to process all of this? If you see this from the possibility here, the first thing you need to do is take the ratio test. Take the ratio test, and then check the ratio, and you can have this tree. Okay, you can check the result. If the series maybe converge when x equals 8, then that's your answer. Stop until there. And if the series converge for x, and that's your result. But when you take the third conclusion, if there is positive number r, which means the ratio has something, then you need to check. Okay, check the convergence, check the divergence, and don't forget to check the endpoints when it's equal to 1. Or rather, not equal to 1, not equal to 1, equal to r in our case here. So again, let me write here. Don't forget to check the endpoints. And a typical question from this power series is finding the radius and finding the interval. The radius means the r, or the ratio, the r. And the interval is the interval of the convergence. Okay, maybe some examples to let you familiar with the power series. Okay, I think I can give examples. Okay, determine the r, or radius of convergence, and interval of convergence, That's the first one. Well, let's say we have these three examples. So to test all these three in power series, start with ratio test. Solve the limit, okay, and check the result, okay, from that. And then later, check the interval. Okay. So the process, okay, to help you, let me write some of the logic or algorithm. First is take the ratio test and solve the limit, and then find R, and then check endpoints, or maybe not check endpoints. Find convergence and divergence. Check the endpoints. And then result, you get the interval. You could try for a while.
So I draw this one.
So it's supposed to be one of the three acts, right?
Yeah.
And you need to take it to the when it's converged, when it's mass level one. And then that removes gradient one. Yeah.
This one.
Yes, correct. And if you multiply two both here, then the radius is 3. Okay?
I got the idea. Masuk alternate, pakai alternate bisa.
Okay, perhaps for the first questions, let me describe in more. So take ratio test. So maybe not all question will be solved, I think. So maybe 2 questions here. So limit and take the ratio. Okay. And then take limit. So this will be x n plus 1, n plus 1, and then 3, n plus 1. And then multiply with n, 3 power of n, and x with power of n, right? Okay. Okay, so next is we can cancel some part. So xn, this is x, this is 3, and this is 3, right? So we have 1 over 3, right? 1 over 3. So limit 1 over 3, I mean right outside here with x. And then we have n over n plus 1. And this will be equal to 1, right? The limit. So this will be equal to 1 over 3 x, right? So by ratio test, remember, this will be converge if or this, right? So we find out that 3 is the radius. So radius is 3. Okay. But we need to check, right? We need to check. So check x equal 3 and x equal -3. Maybe start with x equal 3. Let me erase this first. Check x equal 3. We take into the equations, and the series becomes 3 with power of n, and 3 power of n. So cancel out this 3, right? So we have just a normal harmonic series. P series 1 over n diverge, right? So x equal 3 is not included. And then let me write on the right side here, check the x equal -3. So -3, we take on the x, is being -3 power of n, and 3 of power of n. We can factorize the -1, right? So we can take -1 with power of n and 3 power of n. Or maybe writing this sum in the front, forget to write up. So this will be over n, right? So we can erase we can cancel the 3 power of n, and it will be -1 with power of n, the one that left. And remember, by the alternating series, okay, so by alternating series, this is converged, right? So we need to include the -3. So as a conclusion, remember right at the end. So the series, the power series, is converge when -3 x, or the interval of convergence is -3 to 3 and not included 3. Okay. Okay, any questions? Which one? Yeah. Because the x is only on the top, right? X is on the top. Okay. Remember the question. Okay, any questions? Any questions? So I think for chapter 11, it is going to be like the more you learn the chapter, the chapter 11, the more you learn on the sections, all the methods that previously mentioned, unfortunately we are going to use all of them, mostly. All the definitions, okay? So the next sections, we are going to look on the more like, we are going to include all the methods or the strategy that we've discussed before, right? Especially this power series, the obvious test that need to be done is the ratio test. Okay? And when you check the endpoints, sometimes you need to use some other methods from the previous sections, like the ultimate series, the P series, the geometric series, and so on and so forth. Okay, but I think I will end the lecture up here. Try the other two examples. Try the other two. And I'm trying to set up some assignment for all of you, or just to refresh the chapter 11. Maybe you can, maybe it will be finished before this weekend, so you can start to work on that. Or maybe later. I have given options for you. Choose which time you prefer. It's up to you. If you want to go work this out before holiday or after holiday, that's up to you. Okay, any questions? No? So I think the midterm will be, I think 13th of April. But if we need more review, then it might be 20. It might. Yeah. Yeah, chapter 10 and 11. Okay. 10 and 11. The parametric, right? The polar and 11.
So it's just 20.
Yeah. Okay, it's okay.
2 or 4 weeks. There's no need to postpone the execution.
Yeah. Actually, it's up to you if you decide like maybe 20 is better. Then I think it's okay for 20. Do you think 20 or 13?
I have an exam on the 8th, so
20
20.
better. Okay. Do you think 20? Okay. So maybe in between, if we finish, maybe we need to move on to the next chapter before the midterm. So as usual, we are going to have a feedback. Okay, let's move to here.